Let us continue chemical bonding. In chemical bonding, we discussed valency bond theory. In the valency bond theory is used for explaining shapes of covalent molecules, bond angle, bond length, etc. Another theory is called molecular orbital theory. Next theory is called what in the sense? Molecular orbital theory. This molecular orbital theory is used for explaining bond formation in the molecules. Bond formation in the molecules. Okay. For which it considers linear combination of atomic orbitals. It considers linear combination of atomic orbitals. Linear combination of atomic orbitals. That means atomic orbitals is for atoms electron cloud. They undergo linear combination to give what in the sense? Molecular orbitals. Molecular orbitals is for electron cloud for molecules. Now, so linear combination of atomic orbitals explains about this molecular orbitals and electronic configuration in the molecules. Okay. Now, atomic orbitals on linear combination gives what in the sense? Molecular orbitals. Which atomic orbitals will go for linear combination? Which atomic orbitals will go for linear combination in the sense they should have same energy or nearly same energy, same symmetry, maximum extent of overlap, like this condition should be there. So, which atomic orbitals can go for linear combination in the sense? One point is they should have same energy. That means the atomic orbitals which undergo linear combination should have same energy. Otherwise, nearly same energy. Next, same symmetry. Next, maximum extent of overlap. Then, filling of electrons in molecular orbitals is as like Abba principle, Pauli's principle, and so on. Okay, so now first we will take atomic orbitals. We will take in that first one we will take a SS combination. SS combination will take. We will take SS combination. SS combination in the sense S atomic orbital undergo linear combination with another S atomic orbital from another atom. S atomic orbital from one atom undergo linear combination with S atomic orbital of another atom to give what in the sense? Molecular orbitals. So, now we will take a 1s orbital. We will take. For 1s orbital, here center is what in the sense? Nucleus. Center is what in the sense? Nucleus. 1s orbital is spherical and symmetric. 1s orbital is what in the sense? Spherical and symmetric. This is a symmetric and psi is positive sign. Psi is a positive sign here. Psi is positive sign in the sense it is completely symmetric, we can say. It is completely symmetric. Okay. So it is 1s orbital. This point is nucleus. This point is nucleus. It is symmetric and positive sign is psi. Psi is given positive sign. Psi is given positive sign. Okay. Let us take another 1s orbital. Another 1s orbital will take that nucleus. 1s orbital shape is spherical and symmetric. Okay. For this 1s orbital, psi is positive. Okay. So like this we have taken. For this oneness orbital, psi is positive. Like this we have taken. Okay. Now, these two atomic orbitals undergo linear combination. These two atomic orbitals undergo linear combination. Linear combination in the sense two types possible. One is what in the sense addition overlap. One is addition overlap. Another one is subtraction overlap. Another one is what means subtraction overlap. Two possibilities there. So these two atomic orbitals from two atoms. It is from this oneness orbital from one atom. This oneness orbital from another atom. Another atom in the sense these two atoms combine to give molecule. Okay. So the two oneness atomic orbitals from two atoms undergo linear combination. Linear combination in the sense one is addition overlap possible, another one is subtraction overlap is possible. Okay. So now we will see addition overlap. We will see addition overlap. This oneness orbital, then this oneness orbital. Go for addition overlap. Therefore, here sign is positive. For this sign is positive, addition means that plus will be remaining as plus only. Okay. So here overlapping takes place like this. Then subtraction overlap. This oneness orbital will take that oneness orbital we have taken. For this nucleus we will give. So for this nucleus we are giving. This oneness orbital is going for overlapping with this oneness orbital. Here overlapping possible, and the nucleus we have given. For one atom nucleus, for another atom nucleus. For this oneness orbital, sign of psi is positive, that we will write. For this oneness orbital, sign of psi is positive. Because of subtraction, this plus becomes minus. Subtraction in the sense one orbital should have one sign, another orbital should have opposite sign. So two orbitals should have opposite signs, we can say. Addition overlap in the sense two orbitals should have same sign. Two orbitals should have same sign. Addition overlap in the sense two orbitals should have same sign. Subtraction overlap in the sense two orbitals should have opposite signs. So subtraction overlap in the sense two orbitals will have opposite sign. Addition overlap in the sense two orbitals should have same sign. Okay. Then only addition. So addition overlap in the sense the overlapping atomic orbitals should have same sign. Here positive means here positive. Suppose here negative means here also negative. Subtraction overlap. Subtraction overlap means overlapping atomic orbitals should have opposite signs. So for this positive sign means for this negative sign. Suppose here negative sign means here positive sign. Like this you have to give sign. What is the necessity of these signs? Why we have to give sign? Why should we say here positive means here also positive? Here negative means here also negative. Why should we mention? What is the necessity of here subtraction overlap means opposite signs we are saying no. What does it mean? Addition overlap means same sign we are saying no. What does it mean? What is the meaning of that we will see. Sir, for this we will consider what in the sense interference we will consider. We are considering interference. What is interference? That we will see. Okay. Now we will consider a light comes like this. A light ray comes like this. It is one light ray. Okay. Now we will consider another light ray. Another light ray we will consider. Now both light rays meet at one point. Both light rays meet at one point. at meeting point, okay, at meeting point, how it will be there? At meeting point, both waves meet at one point. Therefore, at this meeting point onwards, we will get a resultant wave. Because both waves meet at this point means at this point we got a resultant wave we are getting. It is one light ray. It is one light ray. Both light rays meet at this point, so that we are getting resultant. How the resultant wave will be there? Sir, now at this meeting point, this number 1 is having crest. Number 2 also is having crest. Then what is the resultant? Resultant is what, in the sense sum of these two crest. This crest is like this, this crest is like this. Now resultant is what? Means sum of these two crest like this. Sir, suppose trough, both are trough, in the sense resultant will be added up. That's all. Resultant will be added up, we can say. Sir, number 1 wave is having trough, at meeting point. Number 2 wave is having trough at a meeting point. What is the resultant? Resultant will be adding up. Resultant will be this. It is a resultant adding up. Okay, that means these two light rays meet at this point. At this point, when they are meeting, while if both are in crest form, then resultant wave will have sum of these two amplitudes. If both have trough, the resultant wave will have sum of these two amplitudes. Sir, suppose first wave is crest, second wave is trough. First wave is crest, second wave is trough. What is the resultant? Resultant is a sum of these two. Sum of these two, in the sense crest will be cancelled by trough. Therefore, resultant may be no wave if these two amplitudes are equal. If these two waves amplitudes are not equal, then resultant wave will have some amplitude, but that amplitude is nothing but subtraction of these two amplitudes. Sir, now here if we see, these two are adding and we are getting this resultant. These two are adding and we are getting this resultant. Therefore, we can say this is called a constructive interference. These two, what we can say, in the sense destructive interference, we can say. Destructive interference, we can say. Constructive interference possible when these two waves are in phase. What is meant by are in phase? In the sense, when at the meeting point, when first wave is making crest, second wave also making crest, then we can say they are in phase. Otherwise, when first wave is making trough, second wave also making trough at the same point, then we can say these two waves are in phase. We can say are in phase in the sense constructive interference. Constructive interference in the sense that indicates a stable situation that we have seen in de Broglie's theory. Sorry, if it is a destructive interference, the waves are out of phase. The waves, we can say, out of phase. Out of phase in the sense when the first wave is making crest at the meeting point, second wave will make trough. Therefore, what happens? Destruction of wave. This results instability for the system. So when the two waves meet with each other, what is the possibility, in the sense constructive interference or destructive interference? That means when the two waves in phase, constructive; when the two waves out of phase, destructive. Like this possible. Okay, now we will see here. Now here we have taken a molecular orbital theory. Here we said atomic orbitals undergo linear combination to give molecular orbitals. Okay, now we have taken 1s atomic orbital from one atom. It is 1s atomic orbital from another atom. Okay, these two atoms combine to give molecule. Okay, these two atomic orbitals undergo linear combination. Here dot indicates nucleus, this plus sign indicates a sign of psi. Psi is called wave function, sign of psi. Okay, this is sign of psi. Here also sign of psi is positive. Like this we have taken. We need not say only positive. If you want to say negative, you can give negative. Okay, but s orbital in the sense it is symmetric. Therefore, sign of psi is either positive, otherwise a negative. That's all. You give positive sign, otherwise a negative sign you give it. You need not give both plus and minus. Okay, here you can give plus, otherwise minus. Similarly, here also, if you want to give plus, you give it, otherwise you give minus. Okay, any one sign only we have to give. Sir. So these two atomic orbitals undergo linear combination. Linear combination means one is addition overlap, another one is subtraction overlap. Addition overlap in the sense both atomic orbitals should have same sign. That means same sign in the same sign. Subtraction overlap in the sense both atomic orbitals, that means overlapping atomic orbitals should have opposite signs. Then only subtraction. Set. So here we are saying the overlapping atomic orbitals, the overlapping part. At overlapping part, waves, this wave and this wave. This electron is having wave nature. This electron also having wave nature. Electrons, that means the waves are in phase, we can say. Okay, at the overlapping part, waves are in phase. Waves are in phase. Then only addition overlap, because the amplitude of both waves will be added up. Okay, waves are in phase means constructive interference. Here overlapping part is having opposite signs. Waves are having opposite signs. Therefore, we can say waves are out of phase. Waves are out of phase, we can say. That see, at the overlapping part, which is overlapping? This orbital and this orbital is overlapping here. That means this wave and this wave is overlapping here. Two waves are overlapping means what? These two waves meet at this point. At this point, both waves are meeting. So at meeting point, both waves are in phase. That is addition overlap. In phase in the sense construction, no. Construction means addition of amplitudes, no. Therefore, here waves are in phase, here waves are out of phase. Therefore, it leads to constructive interference. It leads to destruction. That means this is destructed. The overlapping part is destructed. This overlapping part is constructed. Okay, here overlapping part is constructed. Therefore, how it will be there, we will see here. Here it is nucleus of one atom, it is a nucleus of another atom. Overlapping part is constructed, therefore it is called what in the sense? Molecular orbital is formed. We can say molecular orbital is formed. Okay, here these two atomic orbitals are overlapping here. That overlapping is constructive, therefore this leads to bonding. Therefore, we can say this is bonding molecular orbital. We can call this is as a bonding molecular orbital. Why it is called bonding molecular orbital? Because this orbital and this orbital overlapping here. Overlapping part is constructive. Constructive in the sense this atom and this atom is going for bonding. Therefore, it is resulting what in the sense molecule. Therefore, we are getting molecular orbital. This molecular orbital is favorable for bonding. Therefore, it is called bonding molecular orbital. So, what about this? Here destruction. Destruction means it is not favorable for bonding. Sir, how it will be there? Now we will say one atom nucleus, another atom nucleus. Now this electron, this orbital is this side, this orbital is this side. Okay, this is not favorable for bonding. You see, here nucleus is there. This orbital electron cloud is this side. Here nucleus is there. This orbital electron cloud is almost this side. These two electron clouds are not in between two nuclei. Then is it favorable for bonding? No. Therefore, it is anti-bonding molecular orbital, we can say. Therefore, addition overlap results bonding molecular orbital. Subtraction overlap results anti-bonding molecular orbital cell. Now, here this overlap takes place. Here overlap takes place along the internuclear axis. Therefore, this molecular orbital is a sigma molecular orbital. Here overlapping is taking place along the internuclear axis. Therefore, this molecular orbital is a sigma star molecular orbital. Sigma star means antibonding. Okay. This molecular orbital is obtained by overlapping of two oneness atomic orbitals. Therefore, it is a sigma oneness molecular orbital. This antibonding, this molecular orbital is obtained by subtraction overlap of these two atomic orbitals. Therefore, it is called a sigma star oneness molecular orbital. This antibonding molecular orbital is denoted as sigma star oneness. This bonding molecular orbital is denoted as sigma oneness. Okay, so we got two molecular orbitals we got. So now, how the probability of electron cloud will be there, that point we will see. Here, for this it is a oneness atomic orbital, it is for one atom. Okay, for this orbital, what is the probability of electron cloud means that is chi square. Chi square gives probability of finding electron cloud at a given point around the nucleus in this orbital. In the same way, for this also chi square. This chi square and this chi square, whether it is same or different, that we do not know, because these two are same or different, we don't say. If these two atoms are same, then these two chi square same. If these two atoms are different, these two chi square will be different. Okay, sir. This chi square we say. Now we will see for these two atoms what is the total probability, that we will see. Total probability how much means this chi square plus this chi square, that is equal to 2 chi square. And also we do not know whether these two chi square are same or different, we do not know. Okay, therefore just we will say total probability means sum of these two we will say. Okay, now here we will see the probability. Okay, here we will see the probability for this. Here the wave function chi is equal to addition overlap constructive interference. Therefore, sum of these two wave functions, sum of those two wave functions. Okay, so this wave function, it is wave function of molecular orbital, it is wave function of first atomic orbital, it is a wave function of second atomic orbital. Okay, so if this wave function is here, this wave function is here, this molecular orbital wave function is here. Now we want probability. Probability we want means what we have to do? Square the chi value. So square on both sides. So if you square on both sides, what you will get? Chi square of molecular orbital equal to chi square of one atomic orbital plus chi square of another atomic orbital plus 2 into chi of one atomic orbital into chi of another atomic orbital. Okay, this is what in the sense total probability. We can say total probability like this. In a molecular orbital, total probability is like this. Okay, in this molecular orbital, what is the probability means chi square plus 2 into chi. So now you see that in this molecular orbital, how the probability is there when compared to this total probability. You see here the probability in this molecular orbital is more than that of this total probability. Therefore, this molecular orbital is favorable for bonding, so that it is called a bonding molecular orbital. Okay, now we will see in this molecular orbital. Okay, so here in this molecular orbital, chi is equal to chi of this molecular orbital is equal to chi of this first atomic orbital, then subtraction, therefore minus chi of this second atomic orbital, Now we want a probability here, therefore square on both sides. If we square on both sides, chi square of molecular orbital equal to chi square of one atomic orbital plus chi square of another atomic orbital minus 2 into chi of one atomic orbital into chi of another atomic orbital. Therefore, in this place means between these two nuclei, what is the probability? What is the probability in the sense that probability? Okay, this probability here. This probability here is equal to psi square of one atomic orbital plus psi square of another atomic orbital minus 2 into psi of one and psi of another atomic orbital. Therefore, how the probability is there here in the sense less than these two, this, that means this total probability. Here probability of electron cloud is less than this total probability. Therefore, it is not favorable for bonding. Why? Because here how the probability is there? Less than total probability of these two atoms. Then how do we say it is favorable for bonding? No. So it is, this situation indicates it is not favorable for bonding. Therefore, this molecular orbital is called a anti-bonding molecular orbital. Anti-bonding molecular orbital means we have to say star, we have to say. Okay. Therefore, now we will go for conclusion. Here we are saying SS combination. SS combination means two S atomic orbitals from two atoms undergo linear combination. One is addition overlap gives a bonding molecular orbital, subtraction overlap gives a anti-bonding molecular orbital. Therefore, when two atomic orbitals undergo linear combination, two molecular orbitals possible. One is bonding, another one is anti-bonding. Bonding due to addition, anti-bonding due to subtraction. Sir, this is about what in the sense SS combination we can say. Now, we will see about this sigma oneness. This sigma oneness energy we will see with this oneness atomic orbitals. Okay, now we will compare this energy with these two, we will compare. Okay, how it will be there, that we will see. Now we will take a oneness atomic orbital undergoing linear combination with another oneness atomic orbital to give what in the sense one is bonding molecular orbital, another one is anti-bonding molecular orbital. Now, what about energy of sigma oneness when compared to this oneness atomic orbitals? We will see. Okay, how it is there, that we will see. Now you see here in this molecular orbital, the probability is greater than sum of these two. Therefore, this situation is a more stable situation when compared to these two. Therefore, this is more stable when compared to these two, means this energy will be less when compared to these two. So, therefore, what we are saying in the sense, this energy is less. This energy is less than atomic orbitals. Okay, energy of sigma oneness is less than energy of oneness atomic orbitals. We can say. So, next point we will say, now we'll take this anti-bonding molecular orbital. Here the probability in this molecular orbital, how the probability is there means less than this total probability. Therefore, this situation is leading to instability. Therefore, this stability is less than these two atomic orbitals. Therefore, this energy is more than these two atomic orbitals. Okay, so we can say energy of sigma star oneness is greater than energy of oneness, because it is not favorable for bonding. Therefore, it is not favorable for bonding in the sense this is not stable, so that this energy is more than that of this. Okay, sorry. Next, what about energy of this one and energy of this one, that we will see. Now you see that here probability is high, whereas here probability is low. Therefore, this is more stable, it is less stable. It is more stable in the sense this energy is less, this energy is more, we can say. So we can say that energy of sigma oneness is less than energy of sigma star oneness, we can say. Okay, energy of sigma oneness is less than energy of sigma star oneness, we can say. Okay, next we will take a 2s atomic orbital from one atom, 2s atomic orbital from another atom, either same or different, undergo linear combination to give what in the sense sigma 2s bonding molecular orbital, sigma star 2s anti-bonding molecular orbital. How the energy of these two will be there? Energy of sigma 2s less than energy of sigma star 2s. Okay, energy of sigma star 2s, like this is there. Okay, next we will compare this energy and this energy. Let us compare. Let us compare energy of this and energy of this will compare. Here principal quantum number is 1, whereas here principal quantum number is 2. So that principal quantum number 1 means energy is less, principal quantum number 2 means energy is high. Therefore, we can say energy of sigma 1s is less than sigma star 1s, less than sigma 2s, less than sigma star 2s. Okay, like this will be there, these molecular orbitals. Okay, these molecular orbitals energy will be like this. Okay, next we will see pp combination. Will see p orbitals, p atomic orbitals undergo combination, that will see. Now we are taking pp combination. So far we have discussed ss combination, now we will come for this. Okay, now in this case, now I will take pz atomic orbital. Z is the internuclear axis. Okay, so it is what in the sense pz atomic orbital, z is the internuclear axis. Like this I will assume z is the internuclear axis. Z is called internuclear axis. Like this we will take. Okay, even some cases x axis will be taken as internuclear axis. X axis also will be taken as internuclear axis. Like this also possible. Okay, sir, we have taken Z is the internuclear axis. Like this we have taken. So we have taken pz atomic orbital. We will take another pz atomic orbital. We have taken another pz atomic orbital. Okay, now we will say it is a nucleus of one atom, it is the nucleus of another atom. These two atoms same kind or different kind, any possibility is there. Okay, now we will give sign of psi. Sign of psi we will give here. Sign of psi is suppose positive. Okay, for this sign what means negative, because it is not symmetric. P orbital is not symmetric, s orbital alone symmetric. So for s orbital only you have to give sign of psi either positive, otherwise negative you have to give. For s orbital you give sign of psi is positive, otherwise sign of psi is negative, because s orbital is symmetric. Okay, this p orbital is not symmetric, therefore how the sign will be there means for this lobe if you give positive sign, then for this lobe you must give opposite sign. Suppose if you want to give negative sign, give it, then you give positive sign here, that's all. Okay, then is it here negative sign if you give, here positive sign. Okay, it is not fixed, that means this lobe must be positive. Like this it is not fixed. Okay, so if you give positive you give negative, that's all. Suppose for this lobe you are giving positive in the sense, for this lobe you give negative sign. Sorry. Now these two atomic orbitals undergo linear combination. So what is the possibility? One is addition overlap. Okay, so it is going for addition overlap. This p orbital is going for addition overlap with another p atomic orbital. Okay, so two p atomic orbitals undergo addition overlap. Okay, here what is possibility in the sense addition overlap is possible. Okay, what is the next possibility? Subtraction overlap. Next possibility we can say subtraction overlap, we can say. Okay, so here we are saying that subtraction overlap we are saying. Here we said addition overlap we said, here we are saying subtraction overlap we are saying. Okay, so now what about sign? Sign we have to mention. Okay, first we will say nucleus, we will say here nucleus of one atom, it is a nucleus of another atom. We are saying nucleus, it is nucleus of one atom, nucleus of another atom. Okay, now we have to give sign. Sir, first we will give overlapping lobes sign, we will give it, then we will go for another other lobes. Okay, overlapping lobes sign we will give it. These two lobes are overlapping, therefore for this lobe if you give positive, for this lobe also you must give positive, then only addition. Overlapping lobes, if it has same sign, then addition overlap. So for this lobe if you give negative, then for this lobe also give it negative, then only addition overlap, otherwise no. Same sign should be there. Addition means what? Construction. Construction means what? Waves are in phase. Waves are in phase means what? Meeting point, both waves should make either crest, otherwise trough. Therefore, you give at overlapping part for both lobes, you must give same sign. Okay. Then here positive means here we are giving negative. Here positive means here we are giving negative. Okay. Subtraction overlap we'll see. Here overlapping lobes. Suppose if you give positive here, you must give negative sign here. Negative sign. Okay. Subtraction overlap means overlapping lobes should have opposite signs. Okay. Now it is positive, therefore here negative, therefore here positive. Okay. Now we have given signs for overlapping lobes we have given. Sir, it is going for addition overlap. Therefore, what happens? You see, now we are getting a so and so. We got so and so. Like this we got. Okay. Now it is going for subtraction overlapping. Therefore, how it will be there? You see. Now we will give the nucleus of one atom, nucleus of another atom. Okay. Here nucleus of one atom, nucleus of another atom. Now in between two nuclei, the size of lobe is high. In between two nuclei, size of lobe is high. On either side of nuclei, that means right side of nuclei, size of lobe is less. Left side of this nucleus, size of lobe is less. In between two nuclei, size of lobe is high because this situation is favorable for bonding. Therefore, it is called bonding molecular orbital. Here we'll see. In between two nuclei, two lobes present, that is small and they are not in contact. Therefore, if you draw a plane here, that plane will be nodal plane because probability is 0. So, in between two nuclei, two lobes are there. They are very small enough such that they are not in contact. That means here chi square is 0. Right side of this nucleus, lobe is big. Left side of this nucleus, lobe is big. That means how the probability is there, you see. In between two nuclei, probability is much less. Right side of this nucleus, probability is high. Left side of this nucleus, probability is high. But in this case, in between two nuclei, probability is high. This side and this side, probability is less. Therefore, in between two nuclei, probability is high. Therefore, the situation is favorable for bonding. Therefore, it is called bonding molecular orbital. Whereas it is unfavorable for bonding. Therefore, it is called anti-bonding molecular orbital. So, now here overlapping takes place along the internuclear axis. Therefore, it is sigma molecular orbital. Here overlapping takes place along the internuclear axis. Therefore, it is sigma star molecular orbital. This is resulted by p orbitals. It is resulted by p orbitals. Suppose if it is 2pz, it is also 2pz. Then we will say it is sigma 2pz. It is sigma star 2pz. We can say. So two 2pz atomic orbitals on linear combination gives one is sigma 2pz, another one is sigma star 2pz, two molecular orbitals. Okay. Now pz will undergo linear combination with another pz only, not with px or py. That means symmetry, same symmetry should be there. Therefore, same symmetry should be there, same energy should be there, and overlapping extent also should be high. Sir. Okay. So p orbitals on linear combination, in the sense we said like this. Now, whatever the atom will have 3 p orbitals. How these 3 p orbitals will be there? They will be perpendicular to each other. They will be perpendicular to each other. Okay. Now, in that Z internuclear axis, we have taken Z axis. Okay. Now we will take it is pz orbital. It is pz orbital we have taken. Sorry.